Welcome. In this screencast, we take a look at polar curves with the specific goal of finding their slopes. This is, for some odd reason, not covered in your textbook. So I would like to cover it. It is not difficult, but it is cumbersome. Why? Because to find the slope of a polar curve, we parameterize. We think to ourselves, wait a minute, we just got done talking about parametric coordinates and how easy they make things. And it turns out that y and x are both in terms of r and theta. So why not let theta function as a parameter? And if we do that, then dy dx, the slope of a tangent line to a curve graphed in polar coordinates, is the derivative of y with respect to theta over the derivative of x with respect to theta, where y is r times sine of theta and x is r times cosine theta, just like we learned on a previous slide. Not in this screencast, but in another screencast. Okay? We parameterize in terms of theta, where x and y are the formulas we had from before. So let's find dy dx if r equals 3 minus 2 cosine theta, dy dx at theta equals pi over 2. If you use your calculator to graph this curve, you're going to get a picture something like this. Something like this. This curve is named for a part of the body. It's a cardioid, because it looks like a heart. Attempts to name it a lima beanoid failed. It is a cardioid. At theta equals pi over 2, that's here, right? This is at pi over 2. So we're looking for the slope of that blue line. That's what we're looking for. So how do we do that? The derivative of y with respect to x is the derivative of y with respect to theta over the derivative of x with respect to theta. But what are x and y? Well, y is r sine theta, and x is r cosine theta. So when we find those derivatives, we do it with the product rule. Product rule says that the derivative of this product is derivative of the first times the second plus first times derivative second. The dx d theta is the derivative of this product, and that's derivative of first times second plus first times derivative second, and we evaluate at pi over 2. So what is that? Well, we put in the pi over 2, that's 2 times 1 plus 3 times 0 over 2 times 0 plus 3 times negative 1, and that's a slope of negative 2/3, which seems to be borne out by the picture. So what is most important here? We parameterize in terms of theta. So we have an expression for x, it's a product, and an expression for y, it's a product. We use the product rule to find dy d theta and the product rule to find dx d theta, which is excellent. And then we substitute the value we're interested in, and we're done. Um, let's do r equals -1 plus sine theta at 0. Now, if you use your calculator to graph this curve, you get a limison, and theta equals 0 corresponds to this point, because at theta equals 0, r is -1. So we start at -1 with no rotation. This is the red line whose slope we're looking for. How do you find the slope of that red line? Well, dy dx is dy d theta over dx d theta evaluated at theta equals 0. Y is r sine theta, and x is r cosine theta. So product rule twice here. Dy d theta is derivative first times second plus first times derivative second, and then derivative first times second plus first times derivative second. It's cumbersome and mildly annoying, but it's this process every time we're looking for dy dx. At theta equals 0, this is 1 times 0 plus -1 times 1 over 1 times 1 plus -1 times 0. That's -1. Slope of that red line is -1. Uh, I can't make this any easier because it's always a product rule over a product rule, but I can't make it any harder. It's always a product rule over a product rule. And I hope that that brings some small comfort as we seek to bring trigonometry into the middle of our very last week of Calculus 2. Hope that things are well with you and yours, and we'll see you soon, I hope.